Where are my victims? Where are my students? More. I need more. Maybe one. No. Students, where are my students? Students. No. One minute, I'm in you. Huh? Really? Okay. 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 It's their problem, not mine. Black. It should be white. Okay, let's start. What I would like to do, I would like to show one tiny problem. Okay, you have socks. Transformer. Your middle voltage distribution network. Here, for example, 10 kilovolts high voltage part with customers. Everything fine. Here. And then we had simple one customer. And one funny day, our customer buys generator. In our reality, municipal council decides to rebuild its old heating plant into cogeneration plant. Version 1, version 2. Invest in one turbine. Now many small citizens install solar panels on their roofs, and so on and so on. So here appears second power source. This means that in case of fault, we will have two currents, two energy. One. Oh, okay, we should install circuit breaker here and some protection too. Because in case of fault here, we need to isolate this line. Actually, we can leave for some time other customers with a second source. It's not recommended, but it can be done. One more version to have your middle voltage substation. You may wish to increase reliability of your network. think like this. Rings. What's good in rings type network? You can easily maintain one of the lines while load continues to receive power through the ring outer side. You may have multiple buses, ring kind of network. All this network are sometimes inter-substation. Problem, you have, let's say, substation 1, line, big customer. It's not enough. You cannot maintain this customer by one line. So, you take power, maybe switch like this, you take power from another one. City networks, when you oblige to maintain two sources for fire extinguishing system. Also, so let's try to understand what happens when line is powered or energized from both ends. You have, say, source 1, load in the middle, and source 2. All such kind of scenarios can be reduced to double side fed line. Fault, current from the side of, let's say, system 1 and current from the system 2. Is it clear? Yeah, it's very simple. Now, can I draw a very simple chart? Distance to the fault, current I1. And it depends of distance to the fault. Free phase, line to line. Approximately 866 between them. It's approximately. Okay, it can work. Maybe I'll give myself a bit more space. Is it clear? I assume that this is a middle voltage network. It's isolated neutral for simplicity. Say it's a 10 or 11 kilovolt network. What next? I can draw another chart. It will be I2. Is the line for I2. And Y. Yeah. No, it's one with it. No,
from him, you study next semester and you're getting used to it. Same with you, right?
No.
It's like, you know.
No. We already completed that subject last semester.
We have completed, like, he's enrolled, like, you are enrolled, like, with us.
Yeah, maybe.
Yeah.
Okay. Da. Pum, 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 pum. And it will be maybe something like nope. This is not aesthetic. 3-phase 1-to-1. Something like this. Okay. Let's take a look. A, B, C, D. Let's take a look on protection C. Look here. All this falls in 1-2-1-1. All faults in wire 2 are internal for protection C. Yes? Yes. Where is the minimal internal fault current? Fault 1. It's a 1 is I mean internal for protection C. Okay? So if my protection is sensitive, trip current for it should be at least 10% below 0.1. Yes? Approximately. Here, width gap approximately 3%. This line is E. Trip for protection C. Maybe it will be second zone, not important in this moment. What's important? Is it sensitive? Yes. But I can create this fault. What will be current for this fault through my protection C? I think this one. Yeah. And what will happen? My protection will operate. Falsely. Is this fault internal? No. This is external fault for C. So my protection should not operate. What can I do? Ideas. How do we achieve selectivity? It's time delay. Yeah. Okay. Let's say what? Where I have problem between B and C. Let's say operation time for B should be, let's say, 1/2 second, and for C should be 1 second. Now in case of this fault, what happens? Both start, B and C start. But B sends this connection signal after 1/2 second, this switch disconnects, C returns to its initial state. Agree? Agree. Did I solve problem? Yes. In case of this fault, where is the operation current for B? Actually, I should draw this line. This one is E for B, number 2. And at last, 10%, this is trip current for B. Here it is, this line. If I say I need 10%, what will happen in case of this fault? Oh yeah. Here it is. Here is the distance between trip current of B and fault current. Maybe even this, free phase. B will start, definitely will start. And since it has shorter delay, it will trip. If, see the problem, how it looks. If it's width, maybe here is fault 2. It's minimal internal for B. If I made with time delay selectivity between them, for this fault, this one will be non-selective. If I create selectivity for this fault, this will be non-selective. That end appears too. It is not possible to create selective operation scheme with current and time settings on double fed networks. It's a dead end, you can try. It's impossible to maintain selective operation except a huge difference between current sources. If they are comparable, nothing can be done. What should I do? Ban double side fed lines? Not a good idea. Need solution. What I need? Internal fault, current, operation, error, yeah? External fault, current, operation should be prohibited. So, I need to prevent protection operation for reverse direction faults. If I need to allow operation if energy flows from buses, and I need to prevent operation if energy flows into bus. It's easy to tell, yeah? This joke are garbage. Stop. Theoretical idea. I can plant, let's say, watt meters in the specific way. Like this. Watt meter. Oh! AC and DC watt meter. This one has plus on current and plus on voltage. I plug wattmeter in the way what plus is from bus. A, B, C, and D. A, B, C, and D. Fault 1. Current I1. Current I2. Orange fault number 1. What will wattmeter A show me? Current flow into plus. Yeah? So it will show me something positive, yeah? Good. And what about B? Current I2 flows into plus, so it will show also something positive. And about this one, current flows from plus terminal. Meaning what it will show me what? Minus. And for D, current flows into Oi. More faults to the gut of faults. Fault number 2. A, I1 plus B. Current flows from plus. So I will get negative reading, positive, and positive. Problem solved. What can I see? I see what if I would be able to inhibit protection operation in case of negative power flow, it will solve my problem of double fat lines. Appears what I need something like this. Ka overcurrent relay. T means relay, A amperes. So it's a overcurrent relay. Here should be voltage, and here should be maybe this is not a good way. I will add current. K relay. What means V? Watt. It's a power relay. Relay of power direction. I definitely need to supply also some voltage. If both are telling me yes, I can activate delta T and get my disconnection signal when needed. See the idea? To add additional control. Not only current is bigger. My trip condition will look like current, some setting, and sign of power, maybe at first P, is greater than 0. Huh? We will look at this closer. The first idea was to do what? Familiar device? Where am I? Here. Familiar. Old metal. And what's inside? This one is for isolated neutral networks. This is not good. Nice meter. This meter was imported before the war. It's, I don't know, 89, maybe even 90 years old. But what we see here, voltage coil, current coil, where am I? This is current coil, and disk 1. Second voltage coil, second current coil, and second disk. So-called two-system meters. Such meters were used in first models of relay. What's done? All this this part, counting mechanism, was removed and substituted with simple make contact. This thing is intended for so-called Aaron schematics. Aaron with 2A. Aaron schematics is like this. A phase current, A phase current coil, B phase, C phase current coil. A, U, C, and in the middle they are connected to B phase. Two systematic for iron schematic. Is it good for our business? How do you think? First, power direction relays were based on such meters. But how good? Do you see disadvantage of such schematics? We can try power factor meter. But inside is the same. Okay, this one is for non-symmetrical load. For unbalanced load, it has 3 coils. Yeah, for those who watch outside. Here, power meter. But again, will it be will this fly? Where is disadvantage? What kind of fault can involve in A phase? A phase can be AB or AC, yeah? In case of AB, this voltage will be 0. Relay will not operate. AC, we will get voltage, this voltage. What will happen? These two voltages collapse. Problem with meters in voltage disappear. To prevent this, I need to do something. I need to try to do what? Use non-damaged phase voltage. In case for AB, it's better for me to involve C phase, not damaged. In case for, let's say BC, it's good for me to involve A phase voltage. So for reliability option, so-called 90-degree schematics was incorporated. Idea BC is BAC. Take this as relay voltage, I'm calling A phase relay, and this current as relay current. this such connection is selected for reliability. In case of AB fault, C-phase voltage, third phase voltage will remain. In case of AC, B-phase voltage will remain. Such relay is much more reliable. Meter-based relays found, it happens immediately. They were found unreliable because in case of fault near substation, they failed to operate under voltage. Because of under voltage, they don't have enough voltage to operate. Yeah, but now what kind, if I do so, what kind of operation characteristic will I need? What kind of relay should I order? Very simple analysis. What will be characteristic for the meter? +1, +2. For voltage of relay, if my trip characteristic is simple, P greater than 0, what kind of characteristic will I have? Operate, operate, operate. No operate. Understood? When power is positive, current or current, if a real part of voltage multiplied by conjugated current is greater than 0. This is true in all these hemi-circle. Now question, will relay of such characteristic operate well? Or not? How can we analyze? How can we analyze? Let's look at this. We look here. Internal fault. This is internal fault. +1. Relay equals to BC. Let's assume what we are looking at A-phase relay. This is A-phase relay. A direct sequence. What are, let's say, limits or border cases, or most cases? Fault loop can be full active. If it's a cable network, why not? In case our fault loop is absolutely active, where will be the current? Here is a phase current for such case. If fault loop is pure air, and if fault loop is pure inductive, it's less possible, but okay, let's assume this is EA in case fault loop is full inductive. This section, first quadrant, is an area of all possible for internal fault currents. Understand? Why? Or not? So this is for internal. Now, what about external? Alright? Okay, I'm making mistake. This is internal, green external. Ideal active fault loop is pure active. There will be current vector. Ideas? There can be current vector. If we have ideal active fault loop, ideal active, where it will be. Ideal active, but on external side. Where am I? In case of active photo, angle between voltage and current will be angle between voltage and current. In case of active, look at me. I am active resistance. What's an angle between voltage in current and active resistance? If I apply here voltage, what will be phase shift between voltage and current?
90
90. Inactive.
Zero.
It's inactive. Resistance. 0, of course. So phase shift in active resistance is 0. But current wattmeter, if current flows into this terminal, it shows positive. If current flows into this terminal, what it shows? Negative. There will be angle between current and voltage is 0. But current flows into negative terminal. This means what we will see this 0 but with minus sign, meaning 180 degrees. Minus 0 here is EMF for A phase. Minus 1 is here, 180 degrees. And for coil, we will see this for pure inductive. So all external faults are in this area, in quadrant number 3. And all internal faults are here in quadrant number 1. Go. No. Go. Operate, 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 operate. Idea is, 1 second. For electromechanical relays, there was idea of maximum sensitivity, at which angle minimum power is required for relay to trip. This is vector of maximum sensitivity. If we draw characteristic angle phi, actually minimum required voltage to operate, we will see typical something like this, with this point where U minimal, it's a minimal trip voltage. Minimum voltage required for relay to operate. This one is an angle of maximum sensitivity. MJ, M means maximum, and J utigums, sensitivity. So angle of maximum sensitivity, this line corresponds to the angle of maximum sensitivity. It's and characteristic for basic relays is determined as a normal line to this maximum sensitivity vector. This angle what will be this angle? What will be angle between relay voltage and vector of maximum sensitivity? How many degrees? 45. But where's the voltage, where's the current? Voltage here, current here, current This means what angle is? Negative. This angle is minus 45 degrees. I can try different kind of railway. If I try pure active, I will have this vertical line. This means what I do not operate in case of cable fault. What can I try also? I can try not active power meter, but reactive. I can try railway with imaginary greater than 0. It will give me characteristic like this, also not the baddest one. Possible fell strip, also with this kind, also this one, may cause fell strip. Appears what I need a special craft railway here. I may need something like this. Voltage of my relay, current of my relay, max sensitivity being minus 45 degrees, and at last characteristic like this. Go, here is no go. This is basic. For modern, if you open more modern book, you will see something like this. Go, 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 go. It's a combined characteristic. This radius is trip current. And angle. For older relay it was 180. For some authors propose to increase safety, reduce it to 120, 150 degrees, this opening. It will give you bit of safety. Okay, I would like to create one table. Table. Here is room for one table. One table. Always cautions on sides. Table, where are you? This is not. Oh, I need this one. So, basic standard, so-called 90 degrees connection schematics. In 90 degrees connection schematics, currents are A, B, C. Current. Voltage voltage. E for relay, voltage for relay. So called polarizing voltage. What voltage should be taken into account? DC, CA, and AB. Well working 90 degrees schematics is an alternative version called 30 degrees schematics. Again, A, B, C. Relay. Here, AC, BA, and CB. For line faults, they are equal. For line faults, they are near equal. But there is one problem. If you perform a simulation on both schematics, you will find interesting things. In case of three-phase fault, everything works fine in both cases. In case of line-to-line fault, only in these schematics, all relays operate safely. In 30 degrees schematics, one of the relay sitting on lagging phase will not operate, may not operate. It's not 100% guaranteed, but it's less reliable. In older time, remember current idea of planting two current transformers in A and C to save space and money. Old panels, protection panels, had also two relays, not three, not full set. In case you have set of two relays, 90 degrees is reliable. 30 degrees schematic will always be a fault when it's not reliable, because safely operates only relay on leading phase. Lagging phase may not operate. And that's not all. That's not all what I wanted to say. What I need to say, there there is a small probability of false operation in case we have fault on the client side. Okay, one more. Life is full of surprises. There is one more schematics of
60.
such relays. Nope, 60.
140.
For 60-degree schematics, use two currents. In all the time, have you ever seen American meter? Huh? With two current coils. It has one voltage coil and two current, even in single phase. Because there are two voltages in a house. 110 for sockets and for usual appliance, and 220 for air conditioner, for washing machine, for water heater. They have two voltage in houses. And transformers with secondary winding has earth point in the middle, and on two sides, one 110, one. If you use both, you will have 220. Sockets with two vertical, 110. Sockets with vertical and horizontal, 220. So, it is possible to have a relay with one voltage and two current coils.
They still use this one?
Yes, you may find it. It will be EA minus AB UBC. It's so-called 60-degree schematics. IB minus IC UBA and IC minus IA UCB. Current voltage. What can you tell about this? On the one hand, in case of three-phase fault, it's more sensitive because difference of current will produce square root from 3. In line-to-line for two-phase fault, it operates. But there is one tiny problem. What will happen if I have a fault? On the customer side. have fault on a customer side. What happens? Unlucky me. Line-to-line faults. Line-to-line fault. Transformer with star-delta connection. Fault on the star side. What will happen? Our previous course. Forward. I spent so much time on symmetrical components and forward. I tortured this unlocked transformer. For what? What did we observe during the BC fault? I had a nice stack of ampere meters. What a silence. I don't like this silence. What am I doing here? In case of line-to-line fault on delta side, if fault is on the star side, on delta side, we will see picture like this. Two small current and one big. 1/2, 1/2. A, C, B. This one is for BC. It depends on connection group. Why I'm not hearing it? It's one of the tricky things what will cause you a bonus. In such case, current difference relays do not operate. They do not have sufficient current. So this design will fail if you have delta star transformers. It's not suitable. If you have this network it's grounded neutral, it's not a problem. If you have delta star connection, it will fail. So in European distribution network, this is not usable. In United States, where you have distribution network with grounded neutral, it will work. Next, important moment you should understand. Each real relay in this world, digital or mechanical, or even idiotic student with wattmeter and switch, human relay has its minimal operational voltage. If voltage below this threshold, nothing will happen. Impossible to determine anything. This mean? What this mean? I don't know. Something like this. Angle of maximum sensitivity. Minimal voltage when relay still operates. Inside, 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 inside. What meaning of this characteristic? Nice characteristic. Source. Relay. Relay. Current as a function of distance. Goes like this. What will be voltage? Let's assume we have line, three-phase fault. What will be voltage? Mirror of current. Voltage. At a distance 0, in case of three-phase fault, we will get voltage 0. 0, 0. let's say, minimal voltage. What this mean? What this mean? Our protection will fail to operate in this area. Approximately. This part is so-called blind zone. In case of three-phase fault, protection will not operate because it is not possible to determine direction. What's the most probable scenario for three-phase fault? Your lineman left earthing ring. They started work. What should be done by safety code when linemen do something on line? First, disconnect power switch, then open the disconnector. What is number 3? Check voltage. And number 4, put an earthing ring or grounding at the place of work. This should be done for safety. Next, work can be started. What can happen? And happens many times. Did you linemen go to lunch? Dispatch called them. You finished? Yeah, finished. And tries to switch line on. They didn't finish. They finished morning part. Grounding. Knives or link is still there. What happens? Three-phase fault. At what distance? 0. Here is problem. In case of human mistake, it happens many times. Your protection will not operate. What to do? Old solution was to combine directed protection with instant, non-directed, kind of backup protection. Better, it can be done. But this instant protection is not selective. It operates on reverse direction faults. It's not a best solution. What's the best solution? Do you understand what happens? Modern relays do have memory function. They remember voltage direction before the fault. But this will not rescue us because we have switch on fault condition. Our fault scenario is switch on fault. Memory will be empty. What to do? Good design for protection. First, instant zones. This is zone 1. Maybe more zones. Last, more sensitive zones. Fast, instant zone, more sensitive zone. Next, should have set of old designs had set of 2, modern design have set of 3. Power, direction, relays or functions. Old design didn't have this. So again, A, B, and C currents. Again, A, B, C, and I'm wrong. This one should have B, C, U, C, U, B, U, A. Like this. Set of voltages. Polarizing voltages. Next, and this is for A, for B, and for C. Three-pulse relay forms a signal to terminate. This line is instant. So this part is a zone 1. This is zone 1. Instant. Delayed zone. And for A, for B, for C, and 1, maybe I'll draw it in different color. This is for B, and this one goes for phase A. Delayed zone. Delta. To the three-pulse. Fine. I draw 2 zones protection. One directed instant, and this one directed delay. If you need time-dependent zone, add it. Just extend this line. I might show I showed them in orange. You only will need to extend orange line to the logic of time-dependent zone. But this, what I draw, is incomplete. This will fail in case of three-phase fault on 0 kilometer. To prevent this, one more element should be added. It will be connected here at the point A. One more element. Can I erase this? Do you understand how it works? One more section should be added. In a very basic version, okay, I'll draw a good model. Maybe not. I may first it's complex enough. I will show the idea. In older version with electromechanical relays, we had what? Current, let's say for A phase, and element and delta current voltage. Idea. You have circuit breakers. Take normally closed pair of contacts of your circuit breaker and apply it to the current time relay. Time relay with delayed return, and use it like this. Create a bypass. It has time 1/2 second less. It's so-called speed up bypass. How it works? When switch is off, this relay is energized. When you send an on command, switch goes on. But this path is available for 1 second. What it does is set 0 time delay for second zone, and it bypasses direction logic. So in case of switch on fault, second zone will trip instantly. Why speed up? It makes sensitive second zone to trip instantly. In case you have fault at 0 kilometer, it will operate because power direction function is bypassed. If you have fault at the far end of line, there is no need to wait. In case of switch of fault, protection trips instantly. It was this bypass circuit. It's an old, well-working solution. In modern relays, digital, bit different approach is used because there is no easy way to create a bypass and not necessary second zone. In modern relays, so-called non-selective current protection is employed. Non-selective protection needs free current relay, sensitive, the point R of previous schematics. This is non-selective branch activated for max time is 1 second. This type of schematics with non-selective current protection. Neselektīvi strādājuši maksimāli strāvas aizsardzību. Helps for switch on fault condition. This is for switch on fault. It activates only for short time. It's not activates. It remains active for short time after circuit breaker is activated, switched. There is another approach called speed up after. In after, this circuit is activated by make contact of circuit breaker and start command. If you receive switch on, not start but switch on command, this activates. I do not like this approach, and I'll tell you why. Some moron from lineman can activate switch with button on its drive, not by control knob or SCADA system, but by switch mechanics itself. This will cause malfunction. So this alone activation after, no, should be activated before. Non-selective current protection. It's a way to operate correctly in switch on fault condition. Yeah. Okay, this is for directed overcurrent relay, except one moment. How to coordinate protections. to coordinate protection in shared system employ so-called counter-cross technique. So, watch A1, C1, C2, A2, A3. Here I'm creating time chart this way. How to say, from the, for this way, looking for protection going from remote side. For lower chart, B1, D1 instant zones, then B2, D2 coordinates with B2, D3. Here is my trip time chart for this, for direction from system 2 to system 1. Upper chart from system 1 to system 2. Easy.